Solubility. The term like, dissolve like is often used to describe solubility ionic compounds and polar molecules likely dissolve in polar solvent. Nonpolar molecules dissolve in nonpolar solvent. Water is a polar solvent. Benzene and carbon tetrachloride are nonpolar solvents for dissolving water-insoluble nonpolar molecules. Solubility is the amount of solute that dissolves in a given amount of solvent. Saturated solution. A saturated solution is a solution that has the maximum amount of the solute dissolved in a solvent. Unsaturated solution. An unsaturated solution is a solution that has less than maximum amount of a solute dissolved in a solvent. Next, let's take a look at the supersaturated solution. A supersaturated solution is a solution that contains more than the maximum amount of the solute dissolved in a solvent. Example: if dissolving a substance in water is the endothermic process, the enthalpy is a plus. That means the dissolving process absorbs heat. The process absorbs heat. After the substance reaches saturation at a given temperature, the solution is cooled and the substance becomes precipitating. If the cooling process is slow, the supersaturation occurs. The supersaturation is very unstable. If the supersaturated solution is disturbed, for example, touched by glass rod, the excessively dissolved substance precipitates rapidly. The supersaturated solution becomes saturated solution. Next, let's take a look at the solvation. Solvation describes interactions of a solvent with the dissolved molecules. First, let's take a look at ionic and the polar compound that is soluble in water. Water is a polar solvent. Ionic compounds dissolve in water by forming ion-dipole interactions. Cations interact with the partially negative oxygen atoms, and anion interact with the partially positive hydrogen atoms in water molecules. This model shows how this works. This is the water molecules. This is oxygen and two hydrogen, and this oxygen is partially negative and the hydrogen partially positive. The oxygen partial negative oxygen interact with the sodium ion, the positive sodium ion. The positive hydrogens interact with chloride ion. This negative chloride ion. Non-charged molecules must be able to form hydrogen bonds with water for dissolving in water, like alcohol. Alcohol can form small molecules. Alcohol can interact with, can form hydrogen bonds with the water molecules, so they can dissolve in water. And another example is sugar, table sugar. Table sugar can form hydrogen bond with the water molecule, so the sugar can quickly dissolve in water. The next, nonpolar compound dissolve in nonpolar solvents while forming nonpolar in the molecule forces like London dispersion force. Next, let's take a look at the thermodynamics of solvation. Dissolving a solute in a solvent is a physical process that is accompanied by energy change. Breaking up interactions between solute particles require energy. Forming new interactions between solute and the solvent particles release energy. When solvation releases more energy than that required to separate the solute particles, the overall process is exothermic. Heat is released. Dissolving sodium hydroxide releases heat. This is the example. Then you can see the container is hot or warm. When process of solute particles require more than energy release during the solvation, the overall process is endothermic. Heat is absorbed. Dissolving ammonium nitrate, this process absorbs heat. The container becomes cold. Water-insoluble ionic compounds. Some ionic compounds are water-insoluble because the ionic interactions between ions are very strong and the ion-water interaction forces are not able to break those ionic bonds. For example, calcium carbonate. This salt cannot be dissolved in water because the interactions between calcium ion and the carbonate ion are very strong. Let's take a look at the effects of temperature on solubility. Liquids and solid solutes. Effects of temperature depends on the thermodynamics of dissolving process. Solubility of most solute increases when increasing temperature. The process is endothermic and absorbs heat, such as sodium nitrate. Solubility of some solutes decreases when dissolving, increasing temperature. The process is exothermic and releases heat, like sodium hydroxide. The gas solutes are different. Increasing temperature decreases solubility of gases because the increasing temperature increases kinetic energy of the molecules, therefore increasing evaporation. Effects of pressure on solubility. Pressure changes do not affect solubility of liquid and solid substances, which volumes are not changed by pressure change, but affect the solubility of gases, which volumes are changeable by changing pressure. The high pressure, the high solubility of gases. Next, let's take a look at the concentration units of solutions. The first one is called mass volume percent. This is the definition: mass of solute in grams divided by the volume of solution in milliliter, and multiplied by 100%. Next is a volume percent for liquid solute. Volume of a solute in a milliliter divided by volume of a solution in milliliter multiplied by 100%. Next is called the parts per millions ppm, often used in the field of analytical chemistry. ppm is the parts of a solute in 1 million of parts of a solution. The parts can be mass units, gram, or volume units, milliliter, but the units must be the same for numerator and denominator. ppm, this is the equation. ppm equal parts of the solute divided by the parts of a solution multiplied by million, 10 to 6 order of 6. The last one, let's take a look at the molarity, often used in chemistry, biochemistry. The number of the moles of the solute per liter of solution is the definition of molarity, abbreviated as capital M. Finally, let's take a look at the collective properties. The collective properties are properties of a solution that depend on the concentration of the solute, but not its identity. The first one, the boiling point elevation. The number of solvent particles of the solution is lower than the number of pure solvent liquid. If the solute or solution is non-volatile, the number of solvent of the solution vaporized in the gas phase is fewer than the ones of a pure solvent liquid. As a result, the vapor pressure of the solution is lower than that of the pure solvent liquid. Therefore, the high temperature is required for vapor pressure reach the atmospheric pressure. Boiling point is thus elevated. Freezing point, depression. A solution containing solute has a lower freezing point than the pure solvent. At a given temperature, the intermolecular bond numbers between solvent molecules in a solution is lower than that of a pure solvent. So the chemical potential of a solution is lower than the pure solvent. Take an aqueous solution as an example. An aqueous solution has a lower number of hydrogen bonds than the pure water, so the chemical potential is lower in the solution than pure water, meaning that the solution requires less energy to be in the solid state, like ice, and matte than pure water, so that the melting and the freezing point of a solution is lower than that of water. At 0 degrees, the number of hydrogen bonds between water molecules in a solution is not sufficient for forming ice. Ice is a water molecule crystal, so it's in a liquid phase. Next, let's take a look at the osmotic pressure. Osmosis definition is the passage of water or solvent across a semi-permeable membranes that separate the two solutions. Ions and large molecules are not able to pass through the semi-permeable membrane. Osmetic pressure in an experimental designed two solutions, solution A and solution B, with the same volume by different concentration of dissolvent particles separated by a semi-permeable membrane. Initially, the water flow rate from the lower concentration solution to the high concentrated solution is bigger than the opposite flow rate from the high concentrated solution to lower concentrated solution. more water flows from the low concentrated solution to high concentrated solution than the water flow rate from the solution A to solution B and from solution B to solution A are the same. The high concentrated solution has a larger volume than the lower concentrated solution. The pressure caused by volume difference between two solutions that balance the concentration effect on water flow rate is called osmotic pressure. The greater the concentration difference of dissolvent particles between two solutions, the greater the osmotic pressure.